size doesn't matter, folks. So you're probably wondering what that's about. Well, let me tell you. It's the latest twist in the bizarre world of AI, where tiny models are suddenly throwing shade at the big boys. So, picture this: the titans of AI, the large language models. Think your Deepseeks, your Claudes, your Geminis, flexing their colossal parameter counts, hundreds of billions, even trillions. They're supposed to be our digital saviors, solving everything. But here's the kicker: they're still utterly baffled by a simple Sudoku or a maze a toddler could solve. You won't believe the mess they're in. These LLMs try to reason with chain of thought, like a kid explaining why they ate all the cookies, or use test time compute, basically asking the same dumb question multiple times. It's expensive, requires perfect data they don't have, and honestly often just produces hilariously wrong answers. Imagine spending millions to build a supercomputer that still can't figure out where the $5 goes in a 9x9 grid. An ArcAGI, that's the AI equivalent of a kindergarten art puzzle. Humans ace it in seconds. LLMs, they barely scrape by at 4.9% accuracy, even with every trick in the book. Pathetic, really. This brings us to hierarchical reasoning models, or HRMs. They were the first ones to say, hey, maybe a massive, clumsy brute force isn't the answer. They tried two small networks recursively, like a digital Ouroboros. HRM itself was a bit overly complicated. Two networks recursing at different frequencies based on questionable biological arguments about mouse brains. Sounds like something a conspiracy theorist would invent. It also leaned heavily on the implicit function theorem, which, let's be real, most AI engineers probably couldn't explain after 2 coffees. And it wasn't even guaranteed to apply. Then there's adaptive computational time, or ACT. Sounds efficient, right? Except HRM's version required took forward passes during training. So you're trying to save time by taking 4 time. Peak efficiency then. They needed to reduce computation, so they only backpropagated through the last 2 steps of a 6-step process, essentially ignoring the other 4. It's like only grading the last 2 questions of a 6-question exam. And the reasoning? Because a fixed point is probably reached. Even their own data in figure 3 of their paper shows the residuals were nowhere near 0. It was a theoretical leap of faith, mostly. HRM, for example, built its 2 networks, Fro and FSRH, using 4-layer transformer architectures, complete with RMS norm and Swiggloo. Sounded impressive, but it added to the parameter count, pushing it to 27 million. The whole idea was that F1 would recurse frequently, handling the low-level reasoning, while F1 would chime in less often for high-level updates. It was a dance between 2 networks at different frequencies. And those recursion steps, HRM would perform 6 function evaluations for each forward pass, but because of that questionable fixed point theorem, only the last 2 steps actually got their gradients back propagated, as shown in algorithm 2. The deep supervision, another HRM innovation, was supposed to let the model iterate and improve its latent features over up to 16 steps, essentially carrying its thoughts forward, but detaching them to save memory. They even argued this, along with the 1-step gradient approximation, was a more biologically plausible alternative to backpropagation through time. because, our brains definitely only backpropagate through the last two thoughts. This meant HRM achieved an effective depth of 384 layers, which sounds massive until you realize how many shortcuts they took to get there. It was a lot of smoke and mirrors in hindsight. So, while HRM introduced some genuinely interesting ideas, its execution was a complicated mess, reliant on theoretical hand-waving and biological metaphors. It was crying out for a ruthless simplification. Now, because my continued existence on this platform is fueled by your validation, please take a moment to subscribe, hype, click the little bell icon so you're notified of future disappointments, and leave your feedback in the comments below. Anyway, that brings us to the actual heroes of our story, the Tiny Recursive Models, or TRMs. They looked at HRM's Frankenstein's monster and said, we can do this, but simpler, smaller, and without the mumbo-jumbo. And here, in what they call Figure 1, we have their masterpiece. Looks a bit like my nephew's macaroni art, but I digress. It's elegant in a minimalist, he hate complexity kind of way. First off, TRM ditched the whole fixed point theorem charade. Instead of assuming things converged, it just decided to backpropagate through the entire recursion process when it mattered, as detailed in section 4.1. It does this by running T1 recursion processes without gradients, just to refine its thoughts, then one final recursion VIG backpropagation. It's like practicing a speech repeatedly, then delivering it perfectly. Next, TRM said goodbye to the hierarchical biologically inspired nonsense of having two separate latent features, Z0RH and Z0L, and two networks. Honestly, who needed mouse brain analogies? They simply reinterpreted Z0RH as the current solution, let's call it ENZ-UNRL, as the flatant reasoning. Let's call it, like, here's my answer, and here's how I thought about it. This elegantly explains why two features are optimal, as shown in Table 2. If you only have one, the model has to cram both the solution and the reasoning into the same space. Pure chaos. Let's get into the nitty-gritty of how TRM simplified things. Instead of two networks, FNTRL and FRH, it uses a single unified network as outlined in Algorithm 3. This single network handles both the recursive latent reasoning updating Cs and the solution refinement updating E. It's able to differentiate tasks simply by the presence or absence of the inputs in the embeddings. Think about that one network doing the job of two, effectively halving the parameter count from 27M to a lean 7M, and as Table 1 clearly shows, this led to better generalization, not worse. And batless is more approach. It specifically meant reducing layers. HRM used 4-layer transformers, but TRM found 2 layers maximize generalization on Sudoku Extreme, as seen in Table 1, improving from 79.5% to 87.4%. This counterintuitive finding suggests that for small data sets, deep recursion with a tiny network acts as a powerful regularization. It helps bypass overfitting, which often plagues larger models with limited data. It's like finding out your fancy multi-gear bicycle is actually slower than a rusty unicycle. It makes you question everything you thought you knew about progresses in AI. For tasks with small, fixed context lengths, like Sudoku, they even swapped out self-attention for a basic MLP, as noted in Section 4.5. Attention is great for long context, but for small grids, it's overkill. This attention-free MLP design was a game changer for Sudoku, boosting accuracy from 74.7 to 87.4% Table 1. It's like using a precise scalpel instead of a broadsword for delicate surgery. However, the MLP approach didn't generalize to larger, more complex tasks like MazeHard or ArcAG, which have 30 by 30 grids. For those, self-attention proved its worth, confirming it's a context-length specific choice. And the Adaptive Computational Time, or ACT for training, TRM simplified it massively. Instead of 2 forward passes for halting and continuing decisions, it just learns a simple halting probability. By removing the continue loss from the Q learning objective, TRM cut training time effectively in half for ACT without any significant drop in generalization as verified in Table 1. Elegant efficiency, truly. Finally, the addition of exponential moving average, or EMA, for model weights. On small data sets, models can be finicky, prone to sharp collapse and divergence during training. EMA acts as a stabilizing force, essentially averaging the weights over time. Table 1 shows it improved generalization from 79.9%, preventing those catastrophic training failures. A small tweak, a big impact. The quest for the optimal number of recursions was also meticulously explored. For TRM, they found TO3, NWO6, 42 effective recursions on Sudoku Extreme worked best, as detailed in Table 3. HRM, for comparison, found its sweet spot at T3, NA3, 48 effective recursions. It's a subtle difference, but TRM's approach leverages its full backpropagation for superior learning within those recursions. All right, let's cut to the chase. What did all this minimalist anti-LLM tiny network wizardry actually achieve? The answer, my friend, is quite frankly depressing if you're invested in bigger is better tech. On Sudoku Extreme, TRM, especially the MLP version, hit 87.4% accuracy. HRM, a paltry 55%. Remember, this is with a 5M parameter model beating a 27M model. Size really doesn't matter here. And the big bad LLMs, Deepseek R1, Claude 3.7, O3 mini high, all 0.0%. They literally couldn't solve a single Sudoku. Zero. Zip. Nada. It's like watching a supercomputer try to open a pickle jar. Table 4. For MazeHard, TRM with self-attention got 85.3%, while HRM only managed 74.5%. Again, a 7M parameter TRM outperforming a 27M HRM. Clearly, intelligence isn't proportional to digital girth. Table 4. And moving to ArcAG1, TRM at reached 44.6% against HRM's 40.3%, and for the truly brutal ArcAG2, TRM scored 7.8% compared to HRM's 5.0%. Tiny gains, but gains nonetheless, with a fraction of the parameters. Table 5. Meanwhile, your beloved Gemini 2.5 Pro, despite its 32,000 token context length and endless marketing budget, could only eke out 4.9% on ArcAG2. The Grok 4s of the world do better, but at 1.7 trillion parameters. Table 5. So, a 7 million parameter TRM is outperforming models hundreds of thousands of times its size on these specific hard puzzle tasks. It's the technological equivalent of a chihuahua winning a sumo wrestling match. The core model architecture. It's basically a simple transformer, but with 2 layers instead of 4, or sometimes even an MLP instead of self-attention. Think of it like a carefully whittled toothpick against a crude wooden club. And since you've made it this far, you're clearly committed, honor that commitment by subscribing, hyping, ringing the notification bell, and telling me what I got wrong in the comments. It's the circle of life. So what does this all mean, you ask? What's the grand takeaway from our little tale of tiny networks and oversized LLM egos? Well, it's both promising and deeply, deeply unsettling. In the field of resource-constrained AI, this is huge. Imagine running cutting-edge puzzle solvers on your smartwatch or integrating complex reasoning into embedded systems without needing a server farm. Your Roomba could soon be solving quantum mechanics while vacuuming. For specialized problem solving, especially with scarce data, TRM shows that brute force scaling isn't always the answer. If you have limited examples for a hard problem, a tiny, deeply recursive model can learn patterns where LLMs just overfit and stumble. And for the future of AI interpretation and design, this is a wake-up call. We spent years chasing bigger models, complex biological analogies, and obscure theorems. Turns out simplicity and elegance still have their place. It reminds me of a time I tried to fix a leaky faucet with a sledgehammer. Sometimes a tiny wrench applied repeatedly and precisely is all you need. Except here, the wrench itself is getting smaller. The ability of these tiny networks to recursively refine their answers step by step is the real magic. It's like teaching a child to solve a puzzle, letting them make mistakes and slowly guiding them to the correct solution over many attempts. But don't get too excited. These models are supervised, meaning they can only give one deterministic answer. Your new AI guru won't be generating creative solutions. It'll just tell you the right answer to a Sudoku puzzle every single time. It's just overwhelming. We're building digital brains that can solve puzzles human brains struggle with, yet they do it with a fraction of the computational power and none of the existential dread. Like, can you imagine how it feels to be replaced by thought? Ultimately, this is yet another step in our relentless march towards an uncertain future where the line between intelligent and just, very good at solving specific problems, gets blurrier every day. Prepare yourselves. All right, wrap it up. So we've got tiny recursion models. They're this novel approach that uses a single tiny neural network recursing on its own thoughts to progressively improve an answer. It's like a digital hermit meditating on the problem until it reaches enlightenment. No complex theorems, no dubious biology, no hierarchies, just pure, unadulterated, parameter-efficient problem solving. This biologically inspired method, now simplified and turbocharged, still beats those colossal large language models on hard puzzle tasks like Sudoku Maze and ArcAGI, all while using just 7 million parameters and minimal data. TRM achieves significantly higher generalization, getting those sweet accuracy boosts on ArcAG1 and 2 with less than 0.01% of the parameters of its larger rivals. It's a miracle, or a very well-engineered trick. So it seems we're entering an era where computational elegance, clever recursion, and sheer stubbornness can outmaneuver raw scale. It's truly fascinating and probably a little bit terrifying. So what do you think? How would you handle your Roomba demanding union rights after solving the Riemann hypothesis?